Okay, we're going to do page 10 of the trig functions equation identity addendum, which is about math induction. First it says to generalize the results from part A and B of number 3 and prove your generalization using math induction. So we're going to go up and take a look at the last problem. And in the last problem, remember that we took this like power series. It's like a bunch of trig functions multiplied together, and we found out that it's equal to this expression. And for this one, which goes up to 2 to the 5th power, it's equal to this expression. And we notice there's a pattern here where 2 cubed here becomes 2 to the 4th, and 2 to the 4th here. 2 to the 5th here becomes 2 to the 6th, 2 to the 6th here. So we can write a general expression, which is this one here, where we have sine of x times cosine of x times cosine 2x, cosine 4x, all the way to cosine 2 to the nx. And if we have nx here, n to the nx here, then we have 2 to the n plus 1x here and 2 to the n plus 1 in the denominator here. So we're going to take this general expression and we're going to try to prove this using math induction. Remember that the first step to math induction is we define what the proposition is, and the proposition is equal to this part here, right? We're going to copy this and paste it here. Just make it smaller. So this is the proposition. And we can also say exactly which values of n this is true for. So we could say it's true for n is 1 and above, which would be, we could say, positive integer. Okay. All right. So we've declared what the proposition is, and the next step is we can prove that the first value of n, which is 1, is true. So we'll say p subscript 1 says that left-hand side, sine of x, cosine of x, and how far would it go up to? Let's see. Cosine of 2 to the first n would be cosine of 2x, cosine of 2x, right? Right, okay. And then the right-hand side would be equals sine of 2 to the 2 squared x divided by 2n plus 1, and n plus 1 in this case is 2 squared also. And remember that we already showed this to be true here. Okay, in the previous part. So to prove that that P1 is true, we can use that, right? Basically what we did was we grouped sine x, cosine x together. We made that into 1/2 sine 2x, and sine 2x, cosine 2x, we made that into 1/2 sine 4x, right? So we ended up proving that there. So therefore, P1 is true, okay? Now we are going to prove the step case. And so first we're going to say, assuming that pk is true, what do we know? So now what we can do is we can take this expression here, and we're going to put it here. And now what we're going to do is we'll replace all the n's with k. So this will be k, and this will be k plus 1, and this will be k plus 1. So since we assume that pk is true, we know that that's equal to that. Now we're going to look at the k plus 1th case, okay? So now we're going to write out the k plus 1th case. Oops. the k plus 1th case. I'm going to put it here. So we're going to, instead of just cosine 2 to the kx, we're also going to multiply the next one, which would be cosine 2 to the k plus 1x. And then in the next one, on the right side, we don't know what that is yet, okay? All right, and then we're going to immediately replace this part of it with the part that we assume to be true, which is that. So we're going to put sine of 2k plus 1 divided by 2k plus 1 times cosine of 2k plus 1x. And we know that if we have cosine 2k plus 1 times cosine 2k plus 1, we know that that is related to 2 sine cosine equals sine of 2 theta. Sine 2 sine theta cosine theta is equal to sine 2 theta. If we divide both sides by 2, we'll get sine theta cosine theta equals cosine 2 theta divided by 2. So this is what we're going to do. We're going to take the pink part and we're going to change that into, oh, there's an x here, by the way, sine of 2 times 2k plus 1 x divided by 2 times 2k plus 1. And then if we combine the 2 and the 2k plus 1 and the 2 and the 2k plus 1, we get sine of 2 to the k plus 2 x divided by 2k plus 2. And that is exactly what we wanted to prove. We wanted to prove that the pk case, if we substitute in for k plus 1, we would get the k plus 1th case, and we did. Okay, so we didn't use the right side. We used only the left side, but with some substitution in algebra, we figured out that it is the k plus 1th version of the kth case. So now we can say, thus, and then we could say we could restate the pk part, which is that this okay, is equal to this. If the pk statement is true. Where's pk? Pk is here. Put it really small. Barely fits, right? Okay, if that. Then finally we can say, if P1 is true and pk plus 1 is true, whenever pk is true, then Pn is true for all n is an element of z positive. Okay? All right, moving on to number 5. Use the principle of math induction to prove that this power series is equal to this. Okay, so first thing we need to do is we need to state the p subscript n, and they very conveniently left it all nice and separate for us. So The proposition index n is this thing here. Exactly this, okay? Then what we want to do is look at the base case. The base case is that we take the left-hand side of this and we substitute in n equals 1. If we do, we can see that this is cosine of 2, 1 minus 1, which is 2 to the 0, which is 1. Cosine of 1x. Cosine of 1x is that. So left side is just cosine x, just one term in the power series. And on the right-hand side, we're going to see that if we put n equals 1, we'll have sine of 2x. Sine of 2x is over 2 times the sine of x. So this is 2x. It looks like I wrote 3x, doesn't it? Sine of 2x divided by 2 sine of x. Now let's see if that's true. We're going to modify the right side. So the right side, instead of writing sine of 2x on top, we're going to put in the identity 2 sine x cosine x. And if we do that, we can see that 2 sine x, 2 sine x, 2 sine x on the bottom and top are going to cancel, and we do end up with cosine of x equals cosine x. So thus P1 is true. Okay, so P1 is true, worked. Now we're going to do the step case. So the step case is to take this expression and just replace the n's with k's. So assuming that pk is true, we could say that cosine of x times cosine of 2x times cosine of 4x, blah, 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 cosine of 2k minus 1x equals sine of 2 to the k x divided by 2 to the k times sine of x. Okay? So we know we assume that's true, and so we can use that in our future calculations. So the next step is to say now pk plus 1, which is the cosine of x times, oh, actually, let's just recopy this, okay? So we're going to see if we can show that pk plus 1 is true, only using the fact that pk is true. Okay, so we got this. So we put that, and then we also put the k plus 1th case, which would add one more term to this, which would be 2 to the k x. See what that is equal to. Well, we can take this and we can replace it with this, right? So we'll replace it. We have sine of 2 to the k x divided by 2 to the k sine of x. And that is multiplied times cosine of 2 to the k x. And if we can take the top, sine of 2 to the kx and sine of cosine 2 to the kx, and we can replace that with sine of 2 times 2 to the kx divided by 2. And then we still have on the bottom 2 to the k sine of x. And remember, we can say that because sine of 2 theta is equal to 2 sine theta cosine theta, right? All right. So now let's simplify a little bit. So the top can be simplified into sine of 2k plus 1x divided by 2 to the k plus 1 sine of x. And we've shown that our proposition is true because we've shown that k plus 1, the k plus 1th version, we can start with the left side and end up with the right side analog of the p of k. So now we're going to say thus, this statement, the pk plus 1 statement, which is this, and the right side, which is this, So thus, blah, 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 if the pk is true. Oh, I don't want to do that. I wanted to circle with the scissors. If that. Okay. So, and then finally we can say if p of 1 is true and p of k plus 1 and p of k plus 1 is true whenever p of k is true, then p of n is true for all n that's positive integer. And that's it.